I'm Jens Groth from DFINITY, and I'm going to talk about non-interactive distributed key generation and key resharing. So you may know from earlier presentations of our chain key technology that the internet computer certifies its computation and authenticates messages. And I'm going to talk about how we generate the keys and manage the keys for those certifications and authentications. So each subnet, which is part of the internet computer, has a public verification key. And you should think of this as a long-lived static public verification key. And that makes key management very easy because we will always know a subnet by a unique and permanent public key. So the subnet can then create signatures that verify with respect to this public key on behalf of the canisters that are running on the subnet. So we don't give any single node the secret key that allows you to sign messages. Instead, we actually expect the node to collaborate and sign the messages together. So they all need to be in agreement that this is the message they want to sign, and only if they're in agreement and collaborate can they sign a message. In order to do that, we use threshold signatures. So think of the nodes here as having agreed on a message they want to sign. And every node produces then a share of a signature. Once you have enough shares, so we need to meet a threshold of shares, and here the threshold is 3, then we can combine those shares of signatures to produce a signature on the message that we wanted. Notice the threshold doesn't have to be all of the nodes. It's possible that we can have a slightly lower threshold, and that builds resilience in the system. Even if one node has crashed or the internet connection for that node is unstable, the internet computer still runs, and we can still, on behalf of the subnet, sign messages. However, if too few nodes provide shares, then it's impossible to combine them to get a signature. And that provides resistance against attacks. So the setup now is that the subnet has a public verification key for the threshold signature scheme. And each node has a public share verification key that you can use to verify whether it's producing correct shares of a signature or invalid shares of a signature. And then every node also has a secret share signing key. So the question now is, how do the nodes get these shares of the secret key? So let's first think a little bit about a naive setup, right? So the setup that we traditionally think about when we do secret sharing. And here we imagine there's a trusted third party that we will call a dealer, and the nodes will act as the receivers and get shares of the secret key from that dealer. And this is great if we actually have a trusted third party that we can believe will give us correct shares. But at this point, the nodes have no clue whether the shares that they have received actually correspond to a share of the secret key, or they're just bogus shares, right? The dealer could in principle give them anything. To solve that problem, Feldman back in the 80s suggested the notion of verifiable secret sharing. And here the dealer provides both secret shares to the receivers, but also public key material that they can use to verify and check these shares. In our setting, that public key material will contain the verification key for the signature scheme, and then also the share verification keys for the nodes. And just looking at that public key material, there are easy algorithms to run to check that they all match together and correspond to a correct sharing of the verification secret underlying the verification key. Now, the advantage of this setup with this public key material is that now each node can check its share and compare it to the share verification key and check whether it's correct or not. And of course, if the share is incorrect and invalid, then the node can complain and everybody would actually be able to verify that complaint and see that, ooh, this dealer was cheating. So assuming nobody complains, well, you could say, hope that now we have a correct secret sharing. Now there's one problem with this, which is that each node can verify whether its own secret share is correct or not. But it cannot check whether the other nodes have received correct shares or not. So suppose now there's a node that just doesn't complain, right? And doesn't even either confirm that it's got the correct share, right? And now the remaining receivers, they're in doubt, okay? It could be that this node is just disconnected from the internet or crashed and it will never send them anything. Could be that, in the next second confirmation would arrive or a complaint would arrive. It could also be that that node that's not sending any message is not sending any message because it's actually a malicious node. So we get into these situations where we can get into a gridlock. And we would like to avoid that. And a good way to avoid that would be if we had some way to verify that not only a node's own share is correct, but all of the shares, the whole thing is correct, and guarantee in one go without an extra complaint or acknowledgement phase that all of the shares for every receiver is correct. Okay, so we're going to use something called a publicly verifiable secret sharing. And here the dealer provides both the public key material, but also provides in public encryptions of the secret shares to every node. So every node will have a public encryption key, and the dealer encrypts the secret share for that node with the node's public encryption key. So now everybody can check that there's both public key material and also that there's ciphertext for every node. Finally, the dealer also provides a non-interactive zero-knowledge proof that the whole thing is correct, right? So this non-interactive zero-knowledge proof guarantees that what has been encrypted in these ciphertexts are actually valid secret shares that correspond to the public key material. At this point, there's no longer need for extra interaction. We don't need to have acknowledgement that shares are correct or complaints that they are not correct, because everybody can just verify all this public material and see not only that I, as a node, have received the correct share, but also that every node here has received the correct share that has been encrypted under that node's public key. At the same time, we're not revealing what the shares are, right? So the shares have been encrypted, and therefore we are not revealing what each node's individual secret share is. And the proof is zero knowledge, which means that the proof also is not revealing anything about the secret shares or these secret plaintexts that have been encrypted. So we're going to use this as a fundamental building block in our non-interactive distributed key generation schemes and our non-interactive distributed key resharing schemes. And this is what we call a dealing. Now there's one problem, which is in real life, we don't have this single trusted third party, right? So at this point, the nodes would, from this publicly verifiable secret sharing, the dealing, know that everybody has got a correct secret sharing, and that corresponds to the associated public key material. But what they don't know is whether the dealer is honest or not. And if it's a dishonest dealer, well, then now this dealer also knows all the secret sharings, right? And could start signing messages on behalf of the subnet. So we cannot trust a single entity with generating these secret sharings, right? And therefore we need a distributed key generation protocol. So the setup that we have is that we actually have multiple dealers, and each of these dealers provide a dealing. And then we get security if at least one of those dealers is honest. So we can actually tolerate quite a few bad, malicious dealers. I want to talk a little about how we do resharing as well. Okay, so here, think of a node that already has a share verification key and already has a secret share corresponding to this share verification key. But now this node wants to reshare that secret key. So it wants actually to give another set of nodes shares, subshares, so to speak, of its secret share that correspond to that share verification key. So this we'll call a resharing of an existing share. And it actually works the same way. You can do that with Shamir secret sharing as well. So simply think of this secret key that the node has as an existing share that it wants to share to the receivers. So the node can do that, and in exactly the same way as before, that can also be publicly verifiable. We're just, instead of the public verification key we had before, now we're just thinking of this share verification key as the public key that everybody will know, and they will get shares of this node's secret share signing key. So if we scale this up, suppose we have several nodes that together hold a secret sharing of the public verification key, and they each act as dealers in a resharing and reshare their secret share signing key. Then what happens is actually that the receivers, perhaps a new set of nodes that are supposed to take over this, the computation on this subnet, they will actually get the same public verification key for the subnet, but they will get fresh and new share verification keys that are public and fresh and new secret shares to match those share verification keys. So this is something we call distributed key resharing, right? So the distributed key resharing is also a non-interactive protocol, right? It works pretty much the same way as the key generation protocol. You're just, instead of taking a fresh random secret to share, you're taking an existing share and resharing that. So this is really nice because it means that a subnet can always have a permanent public verification key. But whenever there's a change of nodes, it can actually reshare the secret shares. So the new nodes that are coming in and taking over can get a fresh secret sharing of the secret signing key. So when a subnet starts out, we have some dealers that will create the public verification key together with a secret sharing of the signing key and give that to the first set of nodes running that subnet. But then when we change nodes that are running on a subnet, those nodes can actually give the new nodes a new sharing of the same public verification key. And we can continue doing that over and over again. So using non-interactive key generation and resharing, we get very simple public key management on the internet computer. When the governance system, the neural nervous system for the internet computer, wants to create a new subnet, it simply runs the non-interactive distributed key generation protocol to create a public verification key for the signature scheme that that subnet is going to use, and a matching secret sharing, right, that will give to the nodes. And then the nodes don't actually have to do anything. They don't have to be involved in the protocol in any way. They can just go and get ciphertext that contain encryptions of their secret shares, decrypt those, and then they're up and running. Now, once the subnet is up and running, it can preserve the same public verification key over its entire lifetime of operation. So maybe there will be a change of nodes, maybe there will be at some point less nodes or more nodes, or exchange of nodes because a node has crashed or whatever. But whenever that kind of change happens, you can just reshare the secret key and preserve the same public verification key for the signature scheme. So for an outside user, it looks like this subnet always has the same public verification key, and there's no change whether there's few nodes or many nodes or a change in threshold, lower threshold or higher threshold. It all looks the same. You just get a signature on behalf of that subnet. And you can also do tricks like backing up, for instance, the secret key maybe with a higher threshold and a higher security subnet and things like that. When we have long-lived public keys for the subnet, of course, security becomes really crucial when we think about the corresponding secret signing key, right? Because if at any time during the lifetime of that public verification key an attacker collects enough shares of the secret key, then that attacker would be able to sign messages on behalf of the subnet and impersonate the internet computer. So think about an attacker that sees a set of dealings and stores those dealings, right? And then it might go out and compromise nodes and try to get the decryption keys. Okay, so suppose here attacker first compromises one node and gets the decryption key, and maybe later on the attacker compromises another node and gets the decryption key, and so forth. And once the attacker has enough of those decryption keys, then it can decrypt the old dealings, learn the corresponding secret shares, and now the attacker has enough secret shares to start signing messages on behalf of the subnet. So we want to protect ourselves as much as we can against an attacker that can go out and dynamically corrupt and compromise nodes in the subnet. One way we're going to do that is by using encryption with forward secrecy. So the nodes have this public encryption key that the dealers use to encrypt the shares that the nodes are supposed to use. But instead of just having one static decryption key, the decryption key is actually going to evolve with time. So think of dividing time into epochs. Public key is always the same, but the decryption key evolves. A receiver can update the decryption key to a new epoch and delete the old decryption key. Now, a sender, a dealer in this case, can always encrypt a message to the node, but it will encrypt with respect to a specific epoch. And a receiver with a decryption key for a specific epoch can decrypt ciphertext for this epoch and all future epochs, but it cannot decrypt ciphertext for earlier epochs. And this gives us a measure of security against compromise, right? The past cannot be compromised. So if we have the example before, where the attacker had stored a dealing that the receivers were supposed to get their secret shares from, maybe the attacker compromised one of the nodes and then later on tries to compromise another node to see if it can learn enough decryption keys to decrypt these dealings, then at that point the node may simply have evolved its decryption key and erased the old decryption key for that early epoch where the dealing was first made. And it would be, even if it's completely and fully compromised, it would not be able to give the adversary any useful information. Okay, that decryption key does not exist anymore, and the attacker can therefore not get it and not decrypt the dealings. I want to talk about another type of adaptive attack, right? So forward secrecy is good because it protects the past, but it does not protect us in the future, right? If you get enough decryption keys in a given epoch, you also will know, you can evolve these decryption keys, you will know enough decryption keys also for future epochs. So another security mechanism we have is something that protects against a slightly weaker attack. So here our concern is not whether a decryption key is compromised and learned by the attacker, but if the secret share is compromised and learned by the attacker. That could happen for many reasons. That could be a software glitch, that could be more frequent use of those share signing key and therefore possibility of using side channels to get those secret share signing keys. And the attacker may use exactly the same strategy as before, right? The attacker can maybe with one compromise get the share signing key from one node, and then with another type of compromise get the share signing key from another node, and so forth. And if the attacker collects enough share signing keys, then the attacker can sign on behalf of the subnet. To protect against this kind of attack, we will actually provide what is known as proactive security, which was a strong notion of security that was first proposed in the 90s. So we divide time into epochs. And imagine now we have a set of nodes in a given epoch. They have a sharing of the secret signing key. And maybe the attacker compromises one of the nodes and learns the share signing key that node has. But at the end of the epoch, the nodes, they reshare the secret key and get out a new, fresh sharing of the secret signing key. And then also, once they've done that, they delete the old shares. So now the attacker has one secret share, right? But all the other nodes, they have deleted the old shares. And now the nodes have a new, fresh sharing of the secret signing key. So the attacker will never be able to use the first share that it got from the first epoch to anything. Okay, now during that epoch, maybe the attacker compromises another node and learns the share signing key of that node. But still, it doesn't matter, because at the end of the epoch, if the attacker has not compromised enough nodes and learned enough secret shares, then they will again do a resharing and delete the old shares. So the nodes will keep on refreshing the secret sharing that they have. And the attacker, if the attacker cannot compromise enough nodes within the epoch, within a limited time window, then the shares will be deleted. The remaining shares will be gone for the attacker, and the attacker will never be able to do anything with those secret shares that it actually got in a given epoch. So this is a really cool technique, right? At first, it sounds really counterintuitive that the nodes are going to reshare to themselves, right? So they already have the secret shares. They already have a the secret sharing of the signing key for the public verification key. So why would they reshare? But because whenever they do a resharing, they're also refreshing the shares, and they can delete the old shares. They can actually do this kind of rolling refreshing that really narrows the time window during which an attacker can compromise them. And it's a very interesting security model, because we're actually guarding against compromise of every single node, right? Even if the attacker at some point during the lifetime of this subnet compromises every single node, as long as within each epoch it has only compromised very few nodes, then we're fine. So the security model here is, for instance, that an attacker may, through a glitch or something else, or maybe it compromises a node, but then we wipe that node and reset the system or something like that, right? So, and kick out the attacker again. So the attacker only learns, is able to compromise a few nodes in each epoch, and therefore we get security, even though throughout the lifetime of the system, eventually it may be that every node has at some point been compromised. Taken together, forward security and proactive security provide some complementary security guarantees, right? So forward secrecy guarantees that even if the node is fully compromised, okay, and the decryption key is given to the attacker, then at least the past is not compromised. So as one special example, right, if a node has been on a subnet and learned shares from dealings while it was in the subnet, but then leaves the subnet and evolves his decryption key past that epoch the subnet was in at that time, then there will never be anything that the attacker can get from compromising that node, because it will no longer have relevant decryption keys for that subnet. Now, forward secrecy doesn't provide us guarantees against every type of attack, right? Because once an attacker gets the decryption key for an epoch, then of course the attacker can evolve that decryption key and also learn the decryption keys for future dealings. So to protect the future, we get proactive security. It's a bit weaker notion, right? Because we're not protecting against a full compromise where the decryption key is leaked. But we are protecting against glitches, against malware that can be wiped and things like that, where they're just getting the secret share signing keys. And here we can tolerate compromise in any epoch of a minority of the nodes. Okay, so let's put this together, right? So what we have now is a design for constructing non-interactive distributed key generation protocols and key resharing protocols. And the way it works is to set it up is that a set of dealers provide these dealings, right, that contain public key material, encryption of the shares, and then non-interactive zero-knowledge proofs to prove that everything is correct, right? So it's all publicly verifiable, and anybody who looks at a dealing can see whether it's a correct dealing or not. And given enough dealings from enough dealers, and assuming that one of the dealers is honest and doesn't want to exploit the secret sharing it chose, then the receivers now have a correct and secret sharing of the signing key that corresponds to the public verification key. And the way we use that, as I explained before, right, is that we have the governance system of the internet computer. It can use the non-interactive key generation protocol to generate a public verification key for subnet. And then after that, that subnet can do periodic resharings and still maintain the public verification key, but refresh the sharing so it gets proactive security. And at the same time, if there's a change in guard and new nodes come to the subnet, or some nodes leave the subnet for whatever reason, we can also use the non-interactive resharing scheme to preserve the public verification key, but to set up a new secret sharing of the signing key amongst the new nodes. So I want to talk about the novel research that we have developed that goes into making these non-interactive distributed key generation protocols and key resharing protocols practical. One thing that we have built is a purpose-built compact encryption scheme that has forward secrecy. So compared to other schemes we were looking at, we have significantly smaller ciphertext size. And that matters on the internet computer because all these dealings will be replicated across many nodes, and therefore it's important that they have small size so we don't waste too much storage. A variation of that encryption scheme is a multi-receiver encryption scheme with forward secrecy. What that means is that we are encrypting, so to speak, not just single ciphertext directed at single receivers, but we're creating one large ciphertext that can be used by many receivers in one go. And that saves a significant factor for the parameters we choose, about a factor 4 compared to having many single receiver ciphertexts. Another component we have developed are some very compact non-interactive zero-knowledge proofs that can be used to guarantee we have correct multi-receiver encryption of a secret sharing or secret resharing. In the rest of the talk, I'll be more technical and try to explain, cryptographically speaking, what are the ingredients that go into our protocols. So first, let's talk about the signature scheme that we use. We use BLS signatures, and the setup for that is a triple of cyclic groups of prime order that have a bilinear map, a so-called pairing. So the pairing is a bilinear map that maps from two source groups and into a target group. And in our system, we are using the BLS 12381 curve, where the first source group is the smallest one. Elements in the second source group have about twice the size, the representation, And the target group has about 12 times the size of representation of elements compared to elements in the first source group. We'll also be using a cryptographic hash function that maps arbitrary length bit strings into the first source group. And when we reason about security, we'll be using the random oracle model. Okay, so with this setup, the public verification key is very simple. It's simply the generator of the second source group raised to the secret key. And the signing key is that discrete logarithm. To sign a message, you now compute the hash of the message, which gives you an element of the first source group, and raise that to the secret key. And to verify that, we use the pairing. So we pair the signature with the generator for the second source group and compare that with the pairing of the hash of the message paired together with the verification key. And using the properties of the pairing, you can verify that indeed this should verify as being correct. Those two pairings yield the same result in the target group. As a side note, I note that you can also look at this equation and see, since G2 is a generator of the second source group, that the signature is unique. There's only one possible signature that can satisfy this verification equation. And there are other places on the internet computer where that's a useful fact to know, where we're actually using these BLS signatures to generate unpredictable randomness that is used to drive our consensus protocol. As a side note, it's interesting to observe that the signature is unique. If you look at this verification equation, G2 is a generator of the second source group, and therefore there can only be one signature element, sigma, that can satisfy this verification equation. And the fact that the signature is unique is something that we're using elsewhere on the internet computer. We're using these signatures to generate unique pseudo-randomness, which is something that we're using to drive our consensus protocol. Okay, so that's how BLS signatures work, but how we're going to share the secret signing key. So remember, the secret signing key is just a field element, right? A discrete logarithm of the public verification key. And we're using the classic Shamir secret sharing to share that signing key. When we have a Shamir secret sharing, we can use Lagrange interpolation to recompute the shared secret if we have enough points on the polynomial. So if we have t points on the polynomial, and the polynomial has degree t minus 1, then Lagrange interpolation actually says that we can compute these Lagrange coefficients and reconstruct the secret key as a weighted sum of the shares that we have. Okay, so we don't need to know the shares for every point on the polynomial or for every node in the subnet, but if we have a threshold number of nodes that want to collaborate, they can actually use Lagrange interpolation and compute this linear weighted sum of their shares to get out the secret signing key. So those weights, they do not depend on the shares, they just depend on the indices which nodes are collaborating here. With Shamir secret sharing in mind, let us look at threshold BLS signatures. So the public verification key is just as before. It's a generator for the second source group, raised to this secret key that we want to use. And the share verification keys will be the same generator of the second source group, but raised to the shares that the nodes have. And each node now has a private threshold signing key, a share, which is basically just a point on this polynomial, such that those points correspond to a Shamir secret sharing of the signing key. When a signer wants to produce a share of a signature, they compute the hash of the message and raise it to their secret share. And you can verify that that share is correct in a manner which is very similar to the way that we verify standard BLS signatures. Now suppose we have enough correct shares. So suppose we have a set of T nodes that provide correct shares. In that case, they can actually use Lagrange interpolation in the exponent, so to speak, to construct a signature. So you take all those shares that they have provided, you raise them to the Lagrange interpolation coefficients, and multiply all of those together. And when you do the math in the exponent, you will see that that corresponds to taking the hash of a message and doing this weighted sum of shares, which correspond exactly to the Lagrange interpolation. And what you get out is the hash of a message raised to the secret signing key. In other words, a BLS signature. So for a distributed secret sharing protocol, we use the fact that adding Shamir secret sharings gives us just another Shamir secret sharing, right? That corresponds to adding polynomials together. All of the shares are points on this polynomial. If you add points on the polynomial, you're just getting points on your new polynomial, the sum of the previous polynomials. So if you have a set of dealers that all produce correct secret sharings and give those shares to the receivers, then the receivers can simply add up those sub-shares they get from every dealer, and they would get a share of a combined Shamir secret sharing. And interestingly, because we have this homomorphic properties of the cyclic groups we're working with, the receivers can combine the matching public key material in a similar manner, just by multiplication and exponentiation, and also get the share verification key that every receiver has, and also compute the public verification key. So the distributed key generation protocol now looks like this. We have several dealers that all provide these dealings, right? And the dealings, they have public key material, and we can use these operations, homomorphic operations in the exponent to combine that public key material to construct the share verification keys and also the public verification key for the subnet. And the dealers will be encrypting shares to the receivers. And the nodes that receive these ciphertext, once they have enough ciphertext, right, then they can just combine the corresponding plain text after they decrypt and get out their secret share of the final signing key. The receiving nodes get ciphertext in every dealing from the dealers. They can decrypt those ciphertexts that are intended for them and get out the secret shares corresponding to the dealings. By the additive property of Shamir secret sharing, they can add those secret shares that they have received from the different dealers, and they will get a share that corresponds to their share of the secret key that corresponds to the public verification key for the subnet. Right? So here we're just using the additive property of Shamir secret sharing, that when they add together all these secret shares, the result for all these receiving nodes is that now they have fresh Shamir secret sharing of the secret signing key. For resharing, we have a set of dealers which is nodes already on the subnet, and they already have secret shares of the signing key for the subnet. And what they do in their dealings is they just reshare the secret share that they have. And then it works pretty much the same way as it did for the non-interactive distributed key generation. The receiving nodes will decrypt the ciphertext. They will get out sub-shares from every one of the dealers. But instead of adding the shares, they will actually use Lagrange interpolation. So they will do a weighted sum of those shares. And that will give them a new share of the secret sharing. And they will do the same thing, Lagrange interpolation in the exponent, to combine the public key material from the different dealings and get a new set of share verification keys. And well, turns out that it will be the same public verification key as I had before. So let's think about why this works and why we preserve the public verification key when we do this resharing. So imagine we have a set of dealers, nodes who already have a secret sharing of the secret signing key. So their shares are marked left on this drawing here, S1, S2, S3, and S4. And each of those dealers provides a resharing of its secret share, right? So that gives us some sub-shares that the receivers get. Might be that one of the nodes is crashed and unable to communicate, or it's just late, and we ignore that. All we need from the receiver's point of view is a threshold number of resharings. And then they add these resharings that they have, and they do that with Lagrange interpolation, right? And that gives them their new shares. So the beautiful thing about Shamir secret sharing is that it's preserved under addition, right? But also when you sum with some weights. In this case, we're summing with Lagrange interpolation coefficients as weights. So we know because the dealers already had a secret sharing of the secret signing key, that you would take the Lagrange interpolation coefficients and you sum over their respective shares, then you are indeed going to get that secret signing key. But if you take the same weighted sum of the new subshares that the receivers have, right, then you're also going to get a polynomial with the same degree and a polynomial that hits the same secret. So that shows that we're preserving the secret key when we do this resharing, and therefore also in the exponent preserving the secret key, which means that we also have the same public verification key. So this non-interactive distributed key resharing protocol preserves the public key, but gives fresh shares of the secret signing key to the receivers. With the Shamir sharing and resharing in mind, let's now outline the criteria that we have for our protocol design. First and foremost, we want very simple processes on the internet computer. And that's why we want the protocols to be non-interactive. So there are already existing interactive key generation protocols, and they're also more efficient than what we have developed. But the interaction is problematic, right? Because you suddenly need to have a lot of assumptions about when nodes will send messages, when they're expected to arrive, when they should be expected to complain, acknowledge receipts, and so forth. And sometimes that just doesn't work. And in either case, it's complicated to manage those interactions. Second, we wanted to use the existing setup we have, right? So we're already using pairing-based cryptography because we're using BLS signatures. So therefore, our goal was to construct non-interactive protocols that are pairing-based. We also want reasonable efficiency. Efficiency is not the main goal because we're not using that many distributed key generation and key resharings, but we want it to be reasonable enough for our use case, and therefore we wanted the encryption scheme to be compatible with non-interactive zero-knowledge proofs. And finally, we were interested in something that was reasonable to implement, so we've not hyper-optimized the designs. There are things you could do to optimize performance more, but it would also make the scheme more complicated, both to implement but also to review for security purposes. So here's an initial idea, right, for encrypting shares of Shamir secret sharing. So you would chunk the shares into smaller chunks. Then you could LGML encrypt them with the receiver's public key. And because the chunks are small, you can actually encrypt them in the exponent and later use baby step, giant step, to recover those chunks and then put them together and get the shares. Now, why would you do this complicated encryption process? Well, because we only do exponentiations, right? And that means we can design Schnorr proofs that we have correct secret sharing, that the chunks are decryptable, in other words, sort of like approximate range proofs, and use Fiat Shamir to make those proofs non-interactive. So this encryption scheme would actually be quite nice in connection with non-interactive zero-knowledge proofs. Now, the initial idea does not work, right? Because we want high security. So each node's public encryption key is static and has a long lifetime. It's going to be used many times to decrypt things. So we want chosen ciphertext attack security. And as I explained before, we also want to limit the risk of compromise of secret key material as much as possible. So we want the encryption scheme to have forward secrecy. So again, encryption with forward secrecy, we have a fixed public key, but the decryption key is evolving over time. So after an epoch has passed, a receiver can update the decryption key and delete the old decryption key, and then that decryption key will never be usable again, never recoverable again, and it would be impossible to decrypt old ciphertext. You could only evolve a decryption key forward and encrypt current ciphertext or future ciphertexts. So let's look into how we are constructing our encryption scheme with forward secrecy. So we are using a known idea, which is to use a binary tree encryption scheme. And you can think of that as a variation of a hierarchical identity-based encryption scheme. So there will be 2 to the L epochs, and we will basically place those epochs as leaves on this binary tree. And there will be some public parameters. Just think of those as random group elements in the second source group. And then there's a public encryption key, which is just the generator for the first source group raised to some secret X. Now this looks very much like a malgroup encryption that also has a group element raised to a secret X. But the difference here is that X is not the decryption key, right? Because that would be static, there would be no key evolution. As soon as it would be compromised, you would have broken both past and future ciphertext. Instead, we are masking this X inside the decryption key, and we actually have randomized decryption keys. So decryption key for a leaf contains the path to that leaf. It contains the G1 raised to a random row, and then it has G2 to this secret X, but multiplied with this product of the F's raised to row. Okay? And that product depends on the path down to the node, right? So Fi raised to tau I here. And then the last group element H also raised to row. So that's just for one leaf, this is the key, right? What we need is an evolution, so you can sort of like traverse these leaves and get decryption keys for these leaves of this form. But once you have passed a particular epoch, you should not be able to get the past decryption keys for those leaves. So let me show with an example with a picture how that works. So here's the decryption key for epoch 1. And it will consist of essentially 2 keys. One is the leaf that we see here, and then also a decryption key for this internal node. Okay, so now if you have an encryption for this leaf that you have, then you could just use that decryption key directly. It looks just like a decryption key for the binary tree. If you have a ciphertext addressed to one of the future epochs, so the third or the fourth epoch, then by the structure of this interior decryption key, you can actually derive both the third, a key for the third epoch and a key for the fourth epoch, right? Because you have F2 to the row prime as a free element, and you can decide to multiply that in or not this previous group element. Okay, so if you want to evolve this key here, right, then, well, to evolve it to the third epoch, you would essentially just erase this decryption key for the second leaf, and then you would not be able to decrypt with respect to that anymore. Okay, and you would still have this interior decryption key that would allow you to derive the decryption keys for the third and the fourth leaf. If you wanted to evolve further, now you could derive the decryption key for the fourth leaf and delete the interior decryption key. And now you would not be able to go backwards, but you would still be able to decrypt ciphertext addressed to the fourth epoch. While the decryption keys are actually quite similar to what we've seen before in other forward secure encryption schemes, we have a different structure for the encryption scheme itself. So again, the public parameters are these random group elements F0 to FL and H in the second source group. And the public key is this generator for the first source group raised to some secret X. To encrypt a chunk for a given epoch, we pick some randomness R and S, and let's define F as this product, which is basically the path to that epoch, right? So we write the epoch in binary, and we raise these Fs to those binary digits. Now the ciphertext is then on the form y to the r and g1 to the m, and then we compute g1 to the r and g1 to the s, and in the second source group we compute f to the r and multiply that with h to the s. Okay, so let's see how we can decrypt with that decryption key that corresponds to a leaf. So first, before you decrypt anything, you will verify that this ciphertext is actually well formed. Okay, so you would compute this pairing product equation, and if we look at that a little closer, so z is f to the r and h to the s, so that would give us the same as g1 to the r paired with f. That's what we have on the right-hand side. And we have g1 paired with h to the s, and that's the same as the pairing of s with h. Okay, so we can see that the ciphertext verifies. You can check that it's a well-formed ciphertext just with public operations on it. To decrypt, then we compute this capital M, right? And this long pairing product equation. So we're pairing C with G2 and R with this element from the decryption key, and Z with an element from the decryption key, and S with an element from the decryption key. And then finally, we claim that this capital M is actually the pairing of G1 and G2 raised to the chunk M. And because the chunk is small, we can just do a brute force search for that. Okay, so let's see that this actually works. So let's look at this way we compute capital M, right? So C, that's y to the r and G1 to the m, and y is G1 to the x. Okay, so you'll get from the second part of C, you will get G1 paired with G2 and raised to m, and then you will have this y to the r paired with G2. Okay, and y is G1 to x, so you'll have something with x and with r. And if you look at the second pairing, then you actually have r, which is G1 to the r, and G2 to the x. Okay, so they cancel out these two. But it gives us something new, namely the pairing of r with f to the rho. Okay, that we cancel out when we do the pairing with z, because that gives us G1 to the rho paired with f to the r. But now we have G1 to the rho paired with h to the s. And that's what we cancel out with the last pairing, which pairs s and h to the rho. Okay, so that shows that the ciphertext is, in encryption scheme is correct, and it gives us the right plain text, and is decryptable if the chunk is small enough, right, that you can do a brute force search for it. And that's actually one of the things later on when we do the non-interactive zero-knowledge proof. We use that to prove that the chunks have correct size and they are decryptable with brute force search. I'm not going to go into the security of this encryption scheme here. For that, you would have to see the full paper, but it gives you an impression of what does this forward secure encryption scheme look like. I want to highlight one very important aspect of it. If you look at the ciphertext, it just has 3 source group elements from the first source group and 1 source group element from the second source group. There are no target group elements, and that's unlike previous encryption schemes with forward secrecy, where typically you encrypt a message which is in the target group, and you use those pairings to get forward secrecy. So by necessity, there has to be something in the target group. And the reason we can avoid that is exactly because we have chunking, right? So in our decryption step, we get this plain text out with a brute force search for it. And we can do that because it's a small plain text. So because it's a small plain text, we can sort of like do a meet in the middle in the target group, which is what allows us to embed things in the source groups rather than using the target group. So that's how we get fairly small ciphertext compared to other works on forward secrecy. I want to talk about an optimization of this, because in our system, we also always have multiple nodes that are receivers. So we always know that we're encrypting multiple shares to multiple receivers. And it turns out you can actually combine these ciphertexts. Instead of sending an individual single receiver ciphertext to each receiver, you can do one big multi-receiver encryption. So think of the nodes that are receivers as having public keys, and say they're n receiving nodes. What you can do is you can encrypt chunks to each of these nodes for a given epoch by reusing the randomness. So what you'll do is essentially the same as before, but we'll just use the randomness R and S and Z for all of the ciphertext, right? And you only need to change sort of the delivery of the chunk itself for each individual node. So this looks very simple and straightforward. It's not, because we also have these groups in the second source group, and we have to make very carefully that there's no way you can combine all these elements and extract something. And in particular in the security proof, we actually have to do a simulation where we're starting with a single receiver ciphertext and showing even if all of the other public keys are maliciously chosen by an attacker, you should still not be revealing anything about the chunk that good and benign receivers receiving. So the analysis is more complicated than that. Okay, I'm not going to delve into the non-interactive zero-knowledge proofs and many other details. We have a simple way to make the encryption chosen ciphertext attack secure. We have the non-interactive zero-knowledge proofs for correct secret sharing and correct chunking, so you can actually decrypt the ciphertext. And there's an interest in analysis of that based on rejection sampling. And then, of course, we have security models and security proofs for the full non-interactive distributed key generation protocol and a key resharing protocol. So I want to conclude with what all this buys us, right? So what it buys us is a non-interactive distributed key generation protocol that can create a public verification key for the BLS threshold signature scheme and provide share verification keys and secret shares for the receivers. And then we have the non-interactive distributed key resharing protocol that allows us to preserve the public verification key, but generate new share verification keys and fresh secret shares to a new set of receivers. And that gives us both the flexibility that we can always change the configuration of a subnet, right? If new nodes come in, or new nodes, or there are some nodes that leave the subnet, we can reshare and still have the same verification key, but have a fresh secret sharing for those new nodes. It also buys us the proactive security that we can keep on refreshing the secret sharing and protect ourselves against an attacker that compromises some of the shares within a given epoch.